In some cases, events are completely independent of one another. For example, if you roll a die and get a 6, that doesn't make it any more or less likely that you'll get a 6 if you roll again. Each die roll is an independent event, and there's a probability of 1 out of 6 that you roll a 6 each time. However, other events are dependent. For example, if you draw an ace from a deck of cards and you don't replace it, there's less chance of you drawing an ace on the next draw because there's now one less ace in the deck. Let's start with independent events. We already know that when we roll a die, there's a 1 in 6 probability of rolling a 6. Rolling the die again is a completely independent event. The outcome of the first roll has no influence over the second roll, so there's another 1 in 6 chance of rolling a 6. And so on. If we roll a third time, there's still a 1 in 6 chance of rolling a 6. As we saw previously, if event A is rolling a 6, then its probability is 1 over 6, or 0.167, and each roll of the die is an independent event. No matter how many times you roll the die, the probability of rolling a 6 remains the same on each roll. But what if we want to know the probability of rolling a die 3 times and getting a 1 on the first roll, a 2 on the second roll, and a 3 on the third roll? These are 3 independent events that we'll call A, B, and C. Now we know that each independent event has a probability of 1 in 6, or 0.167. But what's the probability of all 3 events occurring? Now we write that like this. We're looking for the intersection of all 3 events. And we calculate it like this. It's the product of all of the events we want to combine, so we multiply them. So in this case, the probability of rolling a 1, then a 2, then a 3 is 0.167 times 0.167 times 0.167, which is around 0.0047, or 0.47%. Okay, let's look at another way to combine independent events. This time we want to determine the probability of rolling the die once and getting either an odd number or a number that is divisible by 3. Let's call rolling an odd number event A and rolling a factor of 3 event B. Well, let's examine the sample space for this experiment. There's a single die roll, so there are 6 sample points, 1, 2, 3, 4, 5, and 6. The set of sample points that satisfy event A, rolling an odd number, are 1, 3, and 5. And the set of sample points that satisfy event B, rolling a factor of 3, are 3 and 6. Now note that rolling a 3 satisfies both events. It's in the intersection. This sample point is an odd number and a factor of 3. But that's not what we're looking for. We need the probability of rolling an odd number or a factor of 3. In other words, any sample point in either of the 2 sets. Now we call this the union of the sets, and we write it like this. To calculate this, we take the probability of event A, which includes all of the sample points in the set for rolling an odd number, and we add it to the probability of event B, which includes all of the sample points for rolling a factor of 3. However, we need to avoid double counting any sample points that exist in both sets, so we must also subtract the intersection. In this case, there are 3 sample points out of 6 that satisfy rolling an odd number, so that's 0.5, and there are 2 sample points out of 6 for rolling a factor of 3, so that's a third, or 0.33, and there's 1 sample point in the intersection, so we subtract 0.167. So the probability of rolling an odd number or a factor of 3 is 0.633. Now let's consider another scenario. Suppose we hold a lottery based on 5 numbered balls in a bowl. Let's say you have a lottery ticket on which you've chosen numbers 2, 5, and 4. The draw is about to begin and you look at your card and your first pick is 2, and you know that the odds of it being drawn are 1 in 5, or 0.2. The first number is drawn and sure enough it's a 2. Good start. Now you're hoping for a 5. But wait, the odds have changed. We've removed a ball from the bowl and not replaced it, so the probability of drawing a 5 is now 1 in 4, or 0.25. The next ball gets drawn, and you're in luck, it's a 5. Now your hopes for winning rely on the next ball being a 4, and the odds of that are now 1 in 3, or 0.33. Sadly, you're out of luck. The next ball is a 1. Now what's happening here is that the outcome of each event affects the next one. Put another way, the probability of each event is dependent on the previous one. So how would we calculate the overall probability for your ticket winning the lottery? Well, we know that the probability of the first ball drawn being a 2 is 0.2. For the second ball, we need to calculate the probability of drawing a 5, given that we've already drawn a 2. So we're looking for the probability of event B given event A, which we calculate like this: the probability of A and B divided by the probability of A, which is 0.2 times 0.25 divided by 0.2, which is 0.25. And that's what we originally calculated, so we know that the formula works. Now the clever bit is that because our formula is an algebraic expression, we could rearrange it like this, enabling us to calculate the combined probability of event A and event B, allowing for the dependency. So the probability of the first two numbers being a 2 and a 5 is 0.05, or 5%. And we can extend this to calculate the probability for the entire ticket. It's the probability of A times the probability of B given A times the probability of C given A and B, which is 0.2 times 0.25 times 0.33, making the probability of having the winning ticket 0.0165, or around 1.65%.